Hi everyone, welcome to Power Electronics session 13. In the previous session, we discussed about full bridge inverter with R and RL load. Now we discuss pure inductor load, and then we will discuss all the formulas related to full bridge inverter with all the loads. So now if you look at the like a full bridge inverter with inductor load. So here inductor is there, that means inductor is there means like it won't consume any energy. That is why when thyristors are in conduction, either T1 T2 or T3 T4, all the energy will be supplied by the source and it will be stored in the inductor. When diodes are in conduction, D1 D2 or D3 D4, then whatever the stored energy is there, that will supply back to the source. That means average power flow will be 0 in case of pure inductor load. That means here if you look at the conduction angle of each and every thyristor and each and every diode will be same, and only you can see that average power flow will be 0. That means when the respective thyristors are in conduction, that is nothing but like this. T1, T2 are in conduction for the positive half cycle and for positive current. In that case, these two thyristors will be in conduction for T by 4 seconds. Nothing but in degrees, it will be 90 degrees. Okay. Likewise, T3, T4 will be in conduction for negative voltage and negative current for the same time. That means T by 4 seconds, nothing but next 90 degrees. So likewise, diode D1 and D2 will be in conduction for T by 4 seconds for negative voltage but positive current. That means for the 90 degrees it will be in conduction. Likewise, rest of the three diodes, like two diodes, T3, T4 will be in conduction for T by 4 seconds, and that is for negative voltage, positive current, 90 degrees. So here D1, D2 are in conduction for a positive voltage, negative current. Okay, so that's the meaning. All the diodes and thyristors are in conduction for 90 degrees. That means equal conduction. Because of this, you can see that here the average power flow will be 0. And another important thing is constant voltage is given to the inductor, then you will see the current in the inductor will be ramp. Because of this, you can conclude that the current flowing through the inductor will be triangular waveform and voltage across the inductor will be square waveform. So if you look at these things and the waveform will look like this. So voltage across the inductor will be square wave, but current will be following exactly the triangular waveform. And you can see that half of this, like quarter cycle, will be by diodes and rest of quarter cycle in the positive half cycle will be thyristors. Again in the negative half cycle, quarter cycle by diodes, quarter cycle by thyristors. That's the meaning of that. So that's what I told you, that each and every diode and thyristor will be in conduction for 90 degrees or T by 4 seconds. Okay, so this is what. Now we discussed about a full bridge inverter with R load, RL load, then pure inductor load. So if you consider all these loads, then we get waveforms like this. So if you look at R load, okay, if you look at it is R load, then it is RL load, then it is pure inductor load. In all the cases, you can see voltage waveform will be similar. Okay, square wave. That's what I told you, that in case of VSI, output voltage will not depend on the load which is connected to the inverter. But the current waveform will be decided by what load we are connecting to the inverter. That's why you can see the different current waveforms. And this blue color indicates the current and red color indicates the output voltage. You can see that. Now with these things we can conclude few things like so in case of R load, each and every thyristor will be in conduction for T/2 seconds. Okay, thyristors here I can give TH to avoid the confusion. Okay, each and every thyristors will be in conduction for T/2 seconds. That means here 180 degrees. And feedback diodes will not be in conduction at all. That means in 0 degrees. Okay, so here all the conduction is by only thyristors. But in case of RL load, thyristors conduction is always more than diodes conduction. Okay, remember that. So that's what you can see that here this is thyristor by diodes, and again you can see that this duration is by diodes, this is by diodes. Okay, so this is by thyristors, this is by thyristors. That's why you can see that here power flow will be, average power flow from source to load will be positive. Okay, suppose if you are operating the diodes conduction is more than thyristors, means average power flow is negative. That is generally used for inverter acting as a rectifier. That we are not going to discuss here, but generally it will be there in case of electric vehicles, etc. So in this case you can see that average power flow is always 0. That means here it is exactly half of the T/2. That means this is in this T/4 seconds, this is a negative current, positive voltage. Power flow will be negative. In this T/4 seconds, same current and same voltage, but both are positive. That's why positive power flow. Negative power flow, positive power flow exactly cancel each other. That's why average power flow is 0. That's why conduction of the thyristor and diodes exactly equal. That is why power flow will be 0. So these are related to the diode and thyristors conduction. Okay, remember that. Now we will discuss about voltage and current equations. Same loads and same waveforms we are discussing. So here you can see that in all the loads, output voltage waveform is like a square wave. So you know that what will be the square wave? Square wave RMS voltage. Square wave RMS voltage is nothing but maximum value of the waveform. But here, what's the maximum value of the waveform? So V0 RMS is maximum value is VDC. Okay, so that's the first thing. And in case of average inverter is VDC/2 for same source voltage. That is why here by using the full bridge inverter we can get double of the output RMS voltage compared to off-bridge inverter. So we discussed that was the second disadvantage of the off-bridge inverter that we can overcome using full bridge inverter. Then as I told you, I0 RMS value will be equal to V0 RMS by R. This is only applicable for R load. Okay. After this we will discuss about the other loads, but wait for some more time. Okay, next this is the I0 RMS. Okay, so now here as we discussed in the off-bridge inverter, here the waveform is also square waveform. That's why perfect square waveform. Perfect square waveform is nothing but each half cycle is exactly there for 180 degrees. In that case percentage THD will be similar, no difference at all, because percentage THD and distortion factor always depends on the shape of the waveform. Here shape of the waveform is similar to the off-bridge inverter. That's why percentage THD in voltage will be equal to 48.34%. Okay, and here if you want to calculate the distortion factor for the voltage is 0.9. That is nothing but 2 root 2 by pi. So that's what we will get that. So here you can also take that whatever the statements we discussed in off-bridge inverter, same can be applied here. What is that? For the resistive load, current waveform is also exactly similar to the voltage waveform in shape. In that case, current distortion factor and percentage THD in current will be exactly same as voltage equations. But in case of inductor load, voltage THD will be different, current THD will be different because the waveform shape are different. But another thing I told you, this current waveform is somewhat close to the sinusoidal waveform. That means some of the harmonics are reduced in the current waveform because of the inductor. That is actually filtering out some of the harmonics. That is why current distortion factor will be more than voltage distortion factor. That means harmonics are less. That is nothing but THD in current waveform is lesser than THD in voltage waveform. That we need to calculate. We can't simply say that. But in this case, both are 48.34%. Okay, so that's it. And other thing, we can also take for the voltage waveform, we can also take Fourier series as we discussed in case of rectifiers. Same thing here also, but only the difference is the voltage levels. If you take that, for all the loads, V0 equal to sigma n equal to 135, because all the square waves will have only odd harmonics, into 4 VDC by n pi. As I told you that for square wave, 4 by n pi is constant multiplied with the magnitude. Magnitude is VDC into sine n omega t. Okay, so this is the Fourier series for that, and it is starting from 0. That's why no phase shift, nothing will be there. So this is the Fourier series equation for full bridge inverter with RL or L load. But main difference between the full bridge inverter and off bridge inverter is VDC. Okay, in case of off bridge inverter it will be VDC by 2, but here it is VDC. Okay, all the formulas will be same for off bridge inverter and full bridge inverter except the source voltage substitution. In case of off bridge inverter we use VDC by 2. In case of full bridge inverter we use VDC. Okay, remember that. Next we will discuss about the maximum value of the load current in case of RL load, and then after that we will discuss that how to calculate the average value of the source current. That and all we will discuss. But first thing is maximum load current. How to calculate the maximum load current? Using the equations like instantaneous voltage equation across the inductor load. So if you see that either diode D1, D2 or thyristor T1, T2 are in conduction, means voltage across the inductor will be VDC and current will start from here to here like this. So that means in this case what will be the equivalent circuit? It will be like this. Thyristor T1, then resistor, inductor, then T2. Okay, so this will be VDC and this is R, this is L. So now in this case when you turn on this thyristor T1, T2 or maybe diode D1, D2 are in conduction, then current in the circuit will be like this. Okay, either current will be positive or negative based on the which device is in conduction. Now we are operating these switches thyristor T1, T2, like thyristor T1, T2 will be as a switches, means RL load is connected to source voltage, DC voltage. So it's a switching action. How this kind of like KVL equation will be formed here, because we need to calculate here what is the current equation. Okay, so if you want to calculate that current equation, we need to use the KVL equation. What is the KVL equation? In this case, It is like like voltage across or voltage drop across the resistor I0 of t plus inductor voltage L into d I0 of t by dt equal to VDC. Okay, that is in this duration, total duration, the same thing will be there. So as we discussed in rectifiers, if it is the inductor load like this, and then calculating the current in the inductor load will be like this. Calculating current in the inductor load is, it's a kind of like what's that, like kind of like a steady state current. Steady state current is nothing but if you connect these thyristors permanently, then inductor will act as a short circuit for the DC. Then in that case, current in the circuit is VDC by R. So that will be the first portion, steady state current VDC by R. Plus we'll have some transient current, some constant A into e power minus t by tau. So that is general formula for the inductor current. Now we need to calculate A. So what will be the A for this? How to calculate the A for this? We need to use the initial conditions. You can see here when t equal to 0, that means here when the waveform is starting t equal to 0, current in the circuit or inductor will be negative I0, assuming previous pulse is there here. That means before starting, previous pulse is there. If you look at here, I'm using the initial current waveform here to calculate the A, and then we'll substitute here. So that means here initial current is minus Im, that equal to VDC by R plus A into, you can see that here we are substituting t equal to 0. T equal to 0 means what will happen? E power 0. E power 0 is nothing but 1. So that's what we get. So from here A equal to minus Im minus VDC by R. So that's what we get. So now substitute A in this one, then we will get I of t equal to, that means I0 of t equal to VDC by R minus Im into e power minus t by tau, because I am multiplying this one with e power minus t by tau, minus VDC by R into e power minus t by. Okay, so we substituted A in this. Now we can see that our aim is to calculate the maximum inductor load current. So at the time of t by 2 second, what is the current flowing through the inductor? That's a positive Imax. Substitute here and get the Imax. So if you're substituting, that means at t equal to t by 2 seconds, current flowing through the load will be Imax. That equal to, I'm taking common VDC by R from these two cases, that means two terms, that is nothing but VDC by R into 1 minus e power. Now I'm substituting small t equal to t by 2 seconds, that means minus t by 2 tau. Okay, that is what, minus Im into e power minus t by 2 tau. Okay, so that's what we actually substituted current at t equal to t by 2 seconds. Now we can take this term this side and then take common, then finally we'll get Im equal to, that means maximum load current in the inductor load current. Inductor load is Im equal to VDC by R into 1 minus e power minus t by 2 tau by 1 plus e power minus t by 2 time. So this is the maximum load current for inductor load. Okay, remember that. So this can also be taken as maximum load current Im equal to VSI by R into tan H T by 4 tau. This can also be taken into in the form of like hyperbolic functions. Okay, so remember that. Similarly, we can also calculate maximum load current for the inductor load current. Okay, inductor, pure inductor. Okay. In this case, it is very simple. Simple is nothing but equivalent circuit. Equivalent circuit is like here, if T1, T2 are in conduction, or diode T1, T2 are in conduction. In that case, this will be the equivalent circuit. Okay. So now here we need to calculate what will be the current in this circuit and maximum current. You can see that it is very simple means. So load current is actually in this t by 2 seconds is following ramp. If it is following ramp means we can take it like a simple, because the source voltage is connected to the DC only, inductor only. In that case, we can take that simple equation is like inductor voltage equal to L into di by dt. So this is what we can take. But as I told you, in rectifiers, if the load current is or inductor current is following this ramp, then this can be differentiation can be taken as a difference equation. That means change in current divided by change in time. So if you look at this one, in this case, during this time, voltage across the inductor is VDC, and inductance value. Change in current in this t by 2 seconds, how much change is there? Minus Im to Im. That means final value minus of minus initial value. So that will give you 2 times Im. By how much time it is taking? T by 2 seconds. You can substitute t by 2. So from this, maximum value of inductor current for the pure inductor load is, you can take that here 2 this side and t this side, and 2 again comes to the denominator, L comes to the denominator. That is nothing but VDC by 4FL. Okay, we can take like this. You may get the doubt. Here T is there, but how F came into picture. So that is nothing but we can take like time period T equal to 1 by M. Okay, so that's all you get this one. One more equation is there, we will discuss, and then we will complete the full bridge inverters. So one more last topic here, it is nothing but how to calculate the RMS value for other loads like inductive load or capacitor load, whichever it is. You can take that any load. So that means here output voltage will have multiple frequency components, nothing but it is like having square wave. Square wave is nothing but it will have multiple frequency components, nothing but fundamental component, then it will be third harmonic, fifth harmonic, and so on like that. So because of that, load inductance will be different, like inductive reactance will be different, or capacitor reactance is different for different frequencies. That is why impedance offered to the given current will be different. So because of this reason, we can't directly calculate load RMS current equal to load RMS voltage divided by Z, because Z is defined at one frequency only, but multiple frequencies are there, then how to calculate. So in that case, we need to look at the simple equation. So equivalent circuit. Assume we have the load like this, connected in like a capacitor inductor, capacitor, and so on like that. So this is the load connected to the inverter. So in this case, for a given frequency of voltage, assume nth harmonic voltage in the given output. So nth harmonic, then this load draws nth harmonic current, and this resistance will not depend on the frequency. If you exclude the skin losses and all, then this inductive reactance will always depends on the frequency, that is omega n into L. And then you can see that here this inductive capacitive reactance will depend on the frequency, that is nothing but 1 by omega n C. So in this case, you can also take that omega n is nothing but, that means nth harmonic frequency, that's nothing but n times omega, that means an harmonic number multiplied with fundamental frequency. So in this case, you can take that Zn, that means impedance offered to the nth harmonic current. Impedance offered to the nth harmonic current is nothing but Zn, that is nothing but root of so R square plus, here inductive reactance is there, capacitive reactance is there, that's nothing but n omega L, as I told you that omega n is nothing but n omega minus 1 by n omega C whole square. Okay, so this impedance offered to the nth harmonic component, nth harmonic current, is always depends on the harmonic number. So we need to remember this. So likewise here, if you want to calculate the inductive current, RMS value of the load current and all, we can only calculate approximate way. Approximate way is nothing but, what is that? We need to get the kind of different components. What is the different components? Okay, so RMS value of fundamental component. RMS value of fundamental component is nothing but RMS value of fundamental voltage divided by Z1, nothing but substituting n equal to 1 here. Likewise, RMS value of third harmonic component, that's nothing but RMS value of third harmonic voltage divided by Z3, that means n equal to, we need to substitute here 3. So this will also be taken as like from the equation, you can take here V01 divided by 3 into Z2. I will tell you that how exactly this came into picture and all. Once we complete this, we will discuss that also. Then we need to take that fifth harmonic current. Fifth harmonic current is nothing but fifth harmonic voltage RMS divided by Z5. That is nothing but V01 fundamental RMS voltage divided by 5 into Z5. Likewise, we will go with seventh harmonic, and then that is directly nothing but V01 divided by 7 into Z7. Okay, once we got this, means approximately we can calculate I naught RMS equal to approximately. Why approximately means you can calculate other components also, I11, I011, I013, I015, etc. and all, but those will be keep on decreasing, that will not have much value, so that those components won't disturb this RMS value much. That's why approximately you can consider the like a kind of like a dominant components 1 to 7. Then we can calculate RMS value of the load current is, it is like the vector sum of these currents, nothing but I01 square plus I03 square plus I05 square plus I06 7. You can stop here or you can consider I09 also, but that's not important. So this is the RMS value of the load current for any other loads other than resistance. We need to follow like this. Here everything is easy to calculate except Zn. Zn we need to calculate for each n value. N equal to 1 year, n equal to 3 year, n equal to 5 year, n equal to 7 year, like that. So once you got this, then we can calculate lot of other things. That means power consumed by the load is nothing but it is I0 RMS square into resistance. Okay, so that's one value. Then once you got this means, then you can calculate load power factor. Load power factor is nothing but actual power consumed by the load. That's nothing but I0 RMS P0 I0 RMS square into resistance divided by apparent power. That means V0 RMS into I0 RMS. That's what. And once you got this, we can also calculate other thing is nothing but here we can calculate current distortion factor. Current distortion factor is nothing but I01 divided by I0 RMS. Then other thing is you can also calculate percentage THD in current. Once you get this one, we can calculate the percentage THD using the formula. What is that? Percentage THD is nothing but root of 1 by distortion factor square minus 1. Okay, so finally using the power equation, power balance equation is nothing but, so here like power supplied by the source, what's that? VDC IDC equal to power consumed by the load, that's nothing but P0, assuming everything is lossless. Using that power balance equation, we can calculate average source current is nothing but power consumed by the load divided by source voltage VDC. So once you know the RMS value of the load current, we can calculate all these things in case of full bridge inverter or off bridge inverter. Only the difference in case of off bridge inverter, everything is same, but wherever VDC is there, we need to take VDC by 2. Okay, so these are the things with respect to full bridge inverter. Okay, and other thing I told you that how this kind of like V0 how to get that V01 equal to like that means V03, V05, V07 in terms of V1. That's what we are going to discuss now here. Okay, so as we know that V0 for the full bridge inverter is nothing but in Fourier series it is sigma n equal to 1, 3, 5 and so on infinity. It is 4 VDC by n pi sin n omega t. This is what we discussed. So now in this case, assume n equal to 1, nothing but there's a fundamental component. N equal to 1, then what will be the voltage equation? V01 equal to 4 VDC by pi sin omega t. That means n equal to 1, you need to submit here, you need to substitute here. So this is sine wave. So now RMS value of the sine wave is nothing but maximum value divided by root 2. So here 4 VDC by pi whole divided by root 2. That means we will substitute here. So root 2 cancels root 2 times here. That means 2 root 2. So here it is nothing but 2 root 2 by pi into VDC. That's nothing but 0.9 VDC. Okay, so that is the fundamental voltage RMS value for the full bridge inverter. Remember, for our bridge inverter also it will be same, but in place of VDC we need to take VDC by 2. Now substitute n equal to 3. If n equal to 3 means everything is same, we need to substitute n equal to 3 in the Fourier series. That means 4 VDC by 3 pi sine 3 omega t. This is again sine wave, but the frequency is different. When frequency is different, like it is even the frequency is different, sine wave is there means RMS value will be the same. That means same formula. RMS value of this one is nothing but maximum value. This is the entire thing is maximum value. 4 VDC by 3 pi whole divided by root 2. Again root 2 comes in denominator. That's nothing but root 2 cancels 2 root 2 times here. So 2 root 2 by pi into VDC. And this is again same as this one, but except here 3 is remains here. That means 1 by 3. So this is V01. So that means third harmonic component in the full bridge inverter is nothing but V01 divided by 3. So likewise, you can calculate for V05. V05 is nothing but V01 divided by 5 only. V07 is nothing but it is like V01 divided by 7. So that's it. So that's the meaning of that. With this, I'm stopping here. Then remaining things we'll discuss in the next session.